Thank you for the introduction, and my name is Shenwei, and I'm from Nankai University. So Nankai is in Tianjin province, and which is very close to Beijing. So if you have time to visit after the conference, and you can contact me. I'm very honored to be invited here to this prestigious conference and have the opportunity to talk about some recent progress on high-boundedness, which is an active topic in graph coloring. So since this is a comprehensive science conference, I would like to start by telling you some backgrounds on graph coloring. And for those of you who are familiar with the background, please bear with me and you can prove your own theorem in the next 10 to 15 minutes. And then I will move on to the main theme of this talk, high-boundedness, which generalizes the well-known notion of perfect graphs. In this part, I will mostly focus on the famous Gaffer-Sumner conjecture and its quantitative variance. And then I will talk about some new notion called near optimal colorability we introduced last year and present some new results there. And in the first part, I will talk about some proof flavors and ideas. And for those of you who are not working in the field, this may be a bit technical, but I will try to make the presentation as easy to understand as possible. And finally, I will give some concluding remarks. So let me begin with the famous four-color problem. And all of you know that Francis Guthrie proposed the famous four-color problem in 1852. And the problem asks whether it's possible to color a map using only four colors so that adjacent countries get different colors. And here, the requirement adjacent country gets different color is necessary, for otherwise we won't be able to distinguish adjacent countries. So this problem is very easy to state, but it's extremely hard to solve. And at that time, many top mathematicians tried to prove this, to answer this problem, but all failed. Perhaps the most famous example is Minkowski. And one day he walked into the classroom and said to his students that the reason the four-color problem had not been solved was because only the second-class mathematicians were working on it. And he would solve the problem in the next few weeks. But then 3 weeks later, he walked into the classroom again and said to his students with a blue face, and his proof had a flaw. So this turned out to be a very, very difficult question. In fact, it was not until 1976 that Apple and Haken gave a computer-assisted proof. So their proof is not purely mathematical, but heavily relies on computer programs to check thousands of cases. Therefore, many people do not consider this as a real proof. 20 years later, Robertson, Sanders, Seymour, and Thomas gave a new proof. Their proof is, unfortunately, their proof is still relies on computers to check many cases, but their proof simplifies the original proof of Apple and Haken by reducing the number of cases needs to be checked by computers. And their proof was actually implemented in different programming language and tested on different operating systems. So the proof is now widely accepted. And nowadays, the four-color theorem is included in Princeton Companion to Mathematics edited by field medalist Gowers, etc. So next, let me try to give a formal definition of a graph coloring. K-coloring of a graph G is just an assignment of colors from the set of first k integers So here, we view each number here as a color. So a k-coloring is just an assignment of colors from the set to each vertex of G so that adjacent vertices receive different colors. So now imagine you have a graph with hundreds vertices and you are allowed to use 100 colors. Then you can easily color the graph by assigning a different color to each vertex of the graph. So this is not very interesting if you have a lot of color to use. And usually we are interested in coloring a graph using as few colors as possible. And this is the notion of chromatic number. So formally, the chromatic number of a graph G denoted by chi of G is the minimum number of k such that G has a k coloring. And using this language, we can reformulate the four-color theorem as follows. So it states every planar graph has chromatic number at most 4. So here, planar means we can draw the graph on the plane without edge crossing. So the four-color theorem is really a great example that if we impose some structure on the input graph, then we may be able to color a graph using a small number of colors. And more generally, we can ask what are the kind of structures we can impose on graphs to guarantee the graph has small chromatic number. So to be able to answer this question, a first step is to ask what kind of structure makes the graph cannot have a small chromatic number. So a natural obstruction is a large clique. So a clique is just a set of vertices that are pairwise adjacent. So suppose you have a clique of size 10, then you need at least 10 vertices because you need to assign a different color to each vertex in this clique. And more generally, we use this omega of G to denote the size of the largest clique in G, and this parameter is called the clique number. So this omega of G is just the clique number of G. So our arguments shows that the clique number is the natural lower bound on the chromatic number. And a natural question is, what kind of structure we can impose on the graph to make this inequality an equality? So in other words, what kind of structure can guarantee that we can color our graph G use possibly minimum number of colors, the clique number of that graph? So a popular way to impose some structure on a graph is to forbid some small patterns from the input graph. So we have this following notion of H-free. For a set H of graphs, a graph is said to be H-free if it does not contain any member in H as an induced subgraph. So let me explain induced subgraph in the following figure. So here we have a graph of 4 vertices and 5 edges. And if you look at the 3 vertices connected by these 2 blue edges, then this is a path on 3 vertices, P3. And this P3 is induced in our graph. But then if you look at these 3 vertices connected by the 2 blue edges, and this P3 is not induced in our graph because the 2 ends of this P3 are connected by the red edge. So simply speaking, an induced subgraph is just a set of vertices that preserves edges and non-edges in the original graph. So having defined the notion of induced subgraph, we can define an important class of graphs, the class of perfect graphs. We say a graph G is perfect if for every induced subgraph H of G, chi H equals omega H. In other words, we can color every induced subgraph of G using possibly minimum number of colors, the clique number of that subgraph. So here I use this subset to indicate H is a subgraph of G and use the subscript I to stress that this subgraph is induced. So again, to understand which graphs are perfect, maybe it's good to look at which graphs are not perfect. So let me give you two no examples. So for any positive integer t, if you look at a cycle on 2t plus 1 vertices, usually we call them odd holes. And they are complement, and usually we call them odd antiholes. So these two family of graphs are not perfect. For example, if you look at the cycle on 5 vertices, and you can easily see that the clique number is 2, and you need 3 colors to color this graph. So the chromatic number of the C5 is strictly bigger than the clique number, and by definition, the graph is not perfect. So this example shows that a graph is perfect if then it cannot contain any odd hole or odd antihole as induced subgraph. And in 1962, the French graph theorist Claude Burge proposed the famous strong perfect graph conjecture, which essentially says that this converse statement, the converse statement is also true. So formally, he conjectured that if a graph contains no odd hole or odd antihole as induced subgraphs, then the graph must be perfect. And the strong perfect graph conjecture stimulates much development in graph theory because it's connected to many branches of mathematics. For example, polyhedral combinatorics, optimization, and information theory, and so on. Unlike the four-color problem, the strong perfect graph conjecture only took 40 years to solve after being proposed. So in 2002, Chernovsky, Robertson, Seymour, and Thomas announced a proof of the strong perfect graph conjecture, and their paper was published 4 years later in Annals of Mathematics. So now this strong perfect graph conjecture is now become the strong perfect graph theorem. And this is a major achievement in graph theory, and it was awarded the Fulkerson Prize in 2009. And the proof is combinatorial, and it takes 180 pages. So the full proof is very, very complicated. Although the full proof is quite long and complicated, the basic ideas behind it is actually not that complicated. So let me try to sketch the proof in the next slides. So the idea is we want to prove this conjecture by contradiction. So suppose we have a graph contains no odd hole or odd antihole as induced subgraph, and it's not perfect. And then we take such a graph with minimum number of vertices. So we call such a graph a minimum counterexample. The heavy work is to show that the class of graphs containing no odd holes or odd antiholes admits a decomposition theorem, which roughly says that every graph in this class admits a cut set of certain kinds or belong to some basic graph classes. So a cut set is just a set of vertices over which the graph can be decomposed. So you may think of this cut set as the normal subgroup. If you have a group and a normal subgroup, you can decompose the group into the normal subgroup and its quotient group. So something like that. And the basic graph classes are just some well understood graph classes. For example, the class of bipartite graphs. And then you need to show that actually these cut sets cannot occur in a minimum counterexample, and the graphs in basic graphs actually are perfect. So these two facts will give you contradiction to the existence of such a counterexample G. So by the way, this decomposition theorem is a standard tool in the study of structural graph theory, which aims to study the various properties of special graph classes. So it's a very standard tool in studying the property of graph classes. And certainly it's the only way we know so far by proving the strong profit graph conjecture. So is there any questions so far? Okay, so if there's no question, let me move on to the second part of my talk. So the strong profit graph theorem seeks to color a graph with minimum number of colors, namely the clique number of that graph. But in many cases, or in most cases, we cannot be so lucky. So we need more colors than the clique number of that graph. So then we can ask a relaxed question. So maybe what if I allow you to use twice clique number many colors? Can you color that graph using that many colors? Or can you color the graph using omega square number of colors? Or in general, we can ask the following question that can we color a graph G using some function of the clique number? So it can be any function you can imagine. So what do you guess? What's your guess whether this question is yes or no? Does anyone have a guess? Yes. So for basically, so we could restrict ourselves to hereditary graph classes. So then this won't be a problem. So in fact, the answer is no, because of the Michalski construction. And in 1955, Michalski constructed a sequence of graphs Gn, which are triangle free, and its chromatic number can go to infinity. So let's see why this Michel construction gives a negative answer to this question. So let's suppose that such a function f exists, right? So, then the Michalski construction tells us that he has a sequence of graph Gn that is triangle free. So triangle free in our language means the clique number of Gn is at most 2. So now the existence of such function tells us that the chromatic number of G of n is upper bounded by f of 2. But then she also showed that the chromatic number of this graph sequence goes to infinity as n goes to infinity. So this gives you a contradiction. So this construction gives a negative answer for the class of all graphs. And so then the next question is, what if we look at some special graph classes? So in this talk, yeah. So the construction, yeah. So basically, the construction, so the first graph is like you take an edge, so it's the first graph in a sequence, and then the second. So what you do is that so for every vertex, so you create a twin of that vertex. A twin means you add a new vertex here, which has the same neighbors as this vertex. So here, you would add a vertex here, which has the same neighbor as this vertex. And then similarly, you add a vertex here, which is a twin of that vertex. So that has the same neighborhood as this vertex. And then additionally, you add a vertex connects to these two vertices. So simply speaking, you just, for every vertex, you make a twin of that vertex. And then you add another new vertex connects to it, all the twins. So to iterate this process, so you can get like this K2 and C5 and the next one. So you can show that by some simple arguments. This sequence is triangle free, and the chromatic is goes to infinity. So it's always one bigger than the previous graph. Okay, yeah. So I think by the description, I'm sure you can draw the graph by yourself, but let's go over this construction altogether. So what you do is like you make a twin of this vertex, so it connects to this one, these two, right? So I make a twin of that vertex. So it has the same neighbors as this one. So then I make a twin of this vertex, so it has same neighbors as this vertex. And then I make a twin of that vertex, so it has the same neighbor here. Then I make a twin of this vertex like this. And then finally I have a twin of this vertex, so I connect to there. So there are 5 twins of the original 5 vertices. And then I add a final vertex connects to all the 5 twins. So you iterate this and you get the sequence. It depends on what. Yeah, it's it depends on what you mean by far from bipartite. But so if you look at the locally, for example, if you look at the neighborhood of every vertex, then it's independent set, right? Because it's triangle free. So if you look at the neighborhood of each vertex, then it looks like a bipartite graph. But actually, you need a lot of colors to color the whole graph. Okay. Okay, so now, so what I was saying that, so this gives a negative answer to the class of all graphs. So then we can ask what about for special graph classes, whether this function can exist. So this leads to the main notion of this talk, the chi-boundedness. And in this talk, we're always interested in hereditary graph class. So by hereditary, I mean, if you take some graph in your class, then every induced subgraph of that graph is also in the class. Or equivalently, you can think of the hereditary graph classes as H3 for some graph H. So basically, hereditary graph class is the same as by forbidding some fixed graph as induced subgraph. So, so the chi-bound means that a graph class G is chi-bounded if there is a function f such that for every graph in this class, chi of G is at most f of omega G. So let me give you 2 examples. So the first one is bipartite graphs. So by the definition of bipartite graphs, we know the chromatic number and the clique number equals to 2. So this class is chi-bounded, and we can choose such a function f to be identity function. So this is almost trivial. And we know that a graph is bipartite if and only if it contains no odd cycle as induced subgraph. So now if we relax this condition by allowing triangles, but still forbidding other odd cycles as induced subgraph, then we get the class of odd whole free graphs. And for this bigger class, Scott and Seymour proved that this class is also chi-bounded. And we can choose the function f to be 2 to the 2 to the x. So this is a double exponential function in the clique numbers. And one open problem is that we actually do not know whether we can improve this double exponential bound to the single exponential bound. So this is still open. Okay, so as I said, so the hereditary graph classes is just the same as H3 for free graphs by fixing some set H. Yes. That Yeah, this is a good question. Um, I'm not sure, but my guess is no, because you are talking about so the function has to be exactly f, not just upper bound. Bounded, but that's pretty rough. Then the function's bounded has to be normal. It's not known. It's not, so if you are talking about just the upper bound, then you can take some trivial examples, right? Because if it's, say, perfect graphs, then it's obviously f bounded for any f. Lower bound, yes. Yes, yeah, I don't know. I'm not sure. So my guess is, yeah, I'm not sure. Yeah. So we are interested in hereditary graph classes. Obviously, the simplest hereditary graph classes is just by excluding one particular fixed graph, so which we call H3 graphs. The story begins in 1959 when Eldridge proved his famous large girth, large chromatic number theorem using the probabilistic method. So the theorem states that for every positive integer k and g, there exists a graph G with girth at least g and chromatic number at least k. So the girth of a graph is just the length of a shortest cycle in G. So if a graph has large girth, it means it contains no cycles of shorter length. And in particular, the graph is triangle free. So this result is really a generalization of this Michalski construction. And from this result, we can easily deduce the following. So if H contains a cycle, then the class of H-free graphs is not chi-bounded. Because we can simply applying this Eldridge result by setting G to be the girth of H plus 1. So then you get this statement. So this tells us that for the class of H-free graphs to be chi-bounded, H is necessarily acyclic or a forest. And in the 1970s, and Javash and Sumner, they independently conjectured that this necessary condition is also sufficient. So formally, they conjecture that if H is a forest, then H-free graphs is chi-bounded. So this turns out to be a very difficult question, and only very few results are known. Let me walk you through almost all known results in the next few slides. So first of all, this conjecture is true for stars, and this is just an easy application of Ramsey's theorem. And then Javash proved the first non-trivial result. He proved that the conjecture is true for paths. And in his paper, he used this the Javash path argument, which is also very useful for other kinds of problem for path-free graph. And then in 1997, Scott proved that this is true for star subdivision. So take a star, you can subdivide every edge arbitrary number of times. So this is a common generalization of stars and paths. And then in 1994, these two researchers proved that this conjecture is true for all the trees of radius at most 2. And 10 years later, these two researchers proved that it's true for some trees of radius 3. So these trees can be obtained by trees of radius 2 by subdividing once every edge incident with the root. And recently, in 2020, Scott and Seymour proved that this conjecture is true for trees of radius 2 by subdividing some edges incident with the root. So this last result generalizes the first two results. because he says that for every edge incident with the root, we can make an independent decision whether I want to subdivide it or not. So any combination you get satisfies this conjecture. So the first result is just saying that I divide no such edge. And the second result is saying I divide every such edge. So these are pretty much all the known results for this conjecture. So far, the Jaffa-Sumner conjecture concerns the existence of such a function or whether the class is chi-bounded. So it's a qualitative question, but we can also ask its quantitative counterpart. For example, as Asaf already mentioned, maybe could we choose the function to be a polynomial? And in this respect, Louis Esperet made a general conjecture that every chi-bounded hereditary class is polynomially chi-bounded. So here, polynomial chi-bounded is just we can take the function in the definition to be a polynomial. So this is a very general and nice conjecture, but it's too nice to be true. And the last year, a counterexample was found by these three researchers. So their proof is constructive. They construct a specific family of graphs that is chi-bounded, but it's not polynomially chi-bounded. But still, this result does not rule out the possibility that H-free graph is polynomial chi-bounded. So we can consider this polynomial variance of the Jaffa and Sumner. So the question here is if H is forest, whether the class of H-free graph is polynomially chi-bounded. And there is a serious work done by Chinovsky, Scott Seymour, and Spurkle. They first proved that for star forest, the answer is yes. So a star forest is just a forest where each connected component is a star. And then they proved that the answer is yes for double stars. And then they proved that the answer is yes for a forest, which is disjoint union of P4 and any forest the answer for this question is yes. And finally, they prove a quasi-polynomial bound for P5 free graphs. So for P5 free graphs, they were not able to prove a polynomial bound, but only a quasi-polynomial bound. So the bound of the form like is x to the log x. So you may wonder what is so difficult about these polynomial chi-boundedness even for a simple graph classes like P5 free graphs. And one reason is that if a graph class is polynomial chi-bounded, then it implies another very difficult conjectures in extremal graph theory, and Professor Ma has already mentioned in this morning's talk. So the Elder channel conjecture states that if you exclude some fixed graph H as induced subgraph, then your graph has a large clique or stable set. So by large, I mean the size of the clique of stable sets is polynomial in the number of vertices. And in fact, it was a long-standing open problem whether this conjecture is true for P5 free graphs. And it was only resolved last year. So if anyone can prove that P5 free is polynomial chi-bound, then it's a stronger result than this breakthrough result. Okay, now let's move on to the second variant, which I called a linear Jaffa-Sumner. So the question is that for which forest H, the class of H-free graphs is linearly chi-bound. So in other words, can we choose the function to be a linear function? So here we are looking for even functions of better qualities. But it turns out this answer to be easy, and in fact, we have a complete answer for this question. So H-free graphs is linearly chi-bounded if and only if H is an induced subgraph of P4. And so the proof is also not very difficult, and basically it uses lexicographical product of C7 complement. And now let's look at the third version of this Gaffach-Cerner, which I called this optimal version of the problem. So the question is, for forest age, what is the optimal function for this particular graph? As you can imagine that this problem actually becomes harder again. For example, for 4-color problem, it was known that you can always color the planar graph using 5 colors, and the proof is very elegant, only half of pages. But then to improve from 5 to 4 takes another about 80 years. So if you try to derive an optimal bound for chromatic number is a very difficult question. So therefore, it's not very surprising that we only know the answer for our graphs with small number of vertices. So for example, we know that for claw, so the claw is just this complete bipartite graph 1, 3. So for the claw, we know that the optimal function is x squared over log x. So this follows from the classical result on Ramsey number R3T. And for P4, we know that the optimal function is the identity function because P4 free graph is perfect. And for 2P2 free graphs, Wagon in 1980s proved a lower and proved an upper bound on this optimal function. So he showed that the optimal function is at most a quadratic function. So although we cannot, so far we still don't know the optimal function even for 2P2, but for some small value of x, we have the optimal value. For example, for x equals 2, we know the optimal value is 3. So this is an easy exercise. Then we can go one step further. We can ask, what about this optimal value for x equals 3? And this turns out to be 4. So with my postdoc supervisor, we proved that this optimal value is 4. So this actually solves an open problem of Eldridge from the 1980s. Okay, so now let me move on to the third part. So here we introduced a new notion called near optimal colorability, and we say a class of graphs G is said to be near optimal colorable if there is a positive integer C such that for every graph G in the family, chi of G is at most a max of C and omega G. So note that this is a notion between perfectness and linear chi-boundedness, because certainly the max of C and omega G is at most C times omega G. So if a graph is near optimal colorable, then certainly linear chi-boundedness, linear chi-bounded. But it's weaker than perfectness because it only says that if the omega G is large, so it's at least C, then we have chi G equals omega G. So let me tell you how do we discover such a notion. A while ago, we were interested in coloring a particular class of graphs, P6 diamond free graph. So P6 is just a pass on 6 vertices, and diamond is the graph shown on the slides. So from the drawing, you can see why the graph is called diamond. And we were able to show that chi of G is at most omega plus 3. And this bound is tight because there is a famous 27 vertex graph has the clique number 3 and the chromatic number 6, and it's P6 diamond free. So this is a tight bound. However, we did not find any tight example where the clique number is at least 4. So we wonder whether such graph exists. And and it turns out that the answer is no. And then we were able to prove that every P6 diamond free graph has chi of g at most max 6 and omega g. So you can see that this bound is actually better than this bound. And so the proof is really relying on our previous work on the P6 diamond free graphs. So, but we have a more refined structural analysis. Okay, next, let me tell you why this notion is useful. So the usefulness is in designing efficient algorithms for computing the chromatic number. So formally, we have the following proposition. So if we know that testing k colorability is polynomial for every k from 1 up to c minus 1, then we can compute chi in polynomial time. So the proof uses this Lovat's theta function. So the proof is not long, so let me go through the proof in the next slides. So in 1979, Lovat's defined this theta function to be the optimal value of a semi-definite program. For the purpose of this proof, we actually do not need to know what this semi-definite program is. So the important thing here for us is that this parameter can be computed in polynomial time. And moreover, from the definition, we can easily argue that the theta of complement of G lies between omega G and chi of G. Now we just consider two cases depending on whether this parameter is large or not. So the first case is that if theta of complement of G is at least C, then we know that chi of G is at least theta of complement of G. And by our assumption, the chi of G is at most this max bound. And then we know, then by our assumption that C is at most theta of complement of G, and omega is also at most theta of complement of G. So this max is also at most theta of complement of G. So now this inequality chain tells us that the chi of G is equal to theta of complement of G. Therefore, we can compute this chromatic number in polynomial time. And the other case is when the theta of complement of G is less than C. And now, because of this inequality, we know that the clique number of G is less than C. And therefore, this max bound is just becomes C. So we can argue that the chromatic number is at most C. So now, in order to determine this chromatic number, you just run the algorithm for one colorability, two colorability, and up to C minus 1 colorability. And you. Okay, so then we want to know that which graph classes are nearly optimal colorable. And again, we can consider the hereditary graph classes. So the first case is to exclude one graph. And for this problem, the answer is known. And it's the same as the linear chi-boundedness because the proof also is directly from the linear chi-boundedness. And then we can go a step further to consider to exclude the two graphs. So for H1 and H2 free graphs, we can have a almost complete classification of near colorability, except two cases. So the first case is when H is a forest and H2 is a complete graph on M vertices. And this turns out to be equivalent to the Jaffa-Sumner conjecture. And the second case is when H1 is forest and H2 is Kn minus E. So this is a complete graph minus an edge. And to prove this theorem, we have two major parts. So on one hand, we constructed two classes of graphs that are not near optimal colorable. And this allows us to conclude for many pairs of H1 and H2, the corresponding class is not near optimal colorable. On the other hand, we proved that for this particular class of graphs, it is actually near optimal colorable by structural arguments. And so by the proposition on the previous slides, this shows that computing chromatic number for this graph class is polynomial time solvable, and hence answering a question raised by these two researchers. And this year, we continue to investigate the second open case in the previous slides, and we can prove some results for certain graph classes. It's near optimal colorable. And using this result, we can have a complete classification of HK - E free graphs when H has at most 5 verses. Okay, so now I would like to speak a bit about some proof ideas. So firstly, we have a simple reduction. So if the class we are considered is chi-bounded, then the near optimal colorability is equivalent to prove that we can always color the graph using omega number of colors whenever omega is large. So you just take a graph with large clique number, and you show that the chromatic number is equal to that clique number. Then let me tell you some an overall strategy in many proofs of our results. So first of all, you try to find some substructure in your graph by strong perfect graph theorem or some other known results. For example, because our target is to show that this chi of G equals omega of G. And this is our target. So if the graph is perfect, then we are done by definition. So we can always assume that the graph is imperfect. And then we can apply the strong perfect graph theorem to conclude the graph must have an odd hole or an odd antihole. So this can be taken as the substructure C here. Then once you have this substructure, then we can partition the vertices into subsets in terms of their neighborhoods on C. So for example, if you have the C5, so suppose your C is the C5, then you look at the vertices outside. Maybe it has only one neighbor on the C5, maybe it could have 2 neighbors on C5. So you just partition these vertices according to their neighborhoods. And then you try to derive some structure property among those subsets. For example, you maybe argue that actually these two parts are anti-complete, meaning there are no edges between these two parts. And this is very good for coloring because the requirement for coloring is only for adjacent pairs. For non-adjacent pairs, we have no constraints, so they can sort of be colored independently. And then finally, we try to give an explicit strategy to coloring the graph using omega G colors based on structural properties. Now let me expand a bit more detail on the last step, where we try to color the graph based on the structural properties. So the first step is to color some sort of easy part of the graph using omega G colors. So what do I mean by easy? For example, if you have a clique in your graph, and then you certainly can color this clique by these omega G colors. And then we try to extend the partial coloring to the rest of the graph. And in some cases, in order to do this, we need to use some classical theorem in graph theory, which is the Hall theorem. So the Hall theorem states that for a bipartite graph, x and y, if for every subset S of x, the size of the neighborhood of S is at least as large as the size itself, then we can have a matching saturating this X. So by saturation, I mean, you have this bipartite graph X and Y. You have some vertices in X here. By saturating, I mean, you can pair each vertex in X with some vertex in Y and different vertices in X paired to different vertices in Y. So now let me give you, let me illustrate why these matchings are helpful. So imagine now your graph is partitioned into two cliques, X and Y, and X has 5 vertices, and Y has 3 vertices. Okay, so both of them are clique. And then we first try to color this sort of easy part X. We have to color this X. So because it's clique, we know that we need 5 colors, 1, 2, 3, 4, 5, to color X. Okay? And then we try to extend this coloring to Y. So ideally, we want to reuse some of the colors to color the 3 vertices of Y instead of introducing new colors, because our goal is to color the graph using omega G colors. So ideally, we want to reuse the 3 colors here. So then we just ask ourselves, what happens if we can reuse the color? So for example, what if I can reuse the 3 color 1, 2, 3 to color these 3 vertices? Okay. If that happens, then we know that the vertices have the same color are not adjacent. So these two is non-edge, and this is non-edge, and this is non-edge. So this gives us 3 non-edges pairwise disjoint. And this is really a matching in the complement, right? So if you take the complement of this bipartite graph, by which I mean you just flip edges and non-edges. So this is really, what you get is really a matching in the complement. So that's why this Hall theorems is helpful. And finally, in order to use the Hall theorem, you need to verify the condition in the statement of the theorem is satisfied. So if you're lucky enough, you can use the structural information obtained earlier to conclude that this is indeed the case. Okay, so now let me give some concluding remarks. So I hope my talk convinced you that this chi-boundedness is an active topic in graph coloring with many challenging open problems. For example, Alex Scott gave an invited talk at ICM 2022, and his survey in the proceedings of ICM is a nice source. If you're interested, you can always look into there. And another thing is that usually we need many techniques from other areas of mathematics to be able to solve graph coloring problem. For example, these graph theoretical theorems or probabilistic methods or algebraic methods or even topological methods. And Lovatz actually used the topological methods to determine the chromatic number of the Kneser graph. So this is a very famous result. And to give you one more example, last year I was able to find the optimal function for a class of graphs. And to be able to do this, we used this Koenig theorem on the strong duality between matching and covering for bipartite graphs. About future directions, the obvious one is to disprove or prove the Gaffard-Sumner conjecture. And another direction is try to maybe find more connections to L-channel conjecture. So I already mentioned the polynomial chi-boundedness actually implies L-channel conjecture, but maybe the results and the techniques from L channel conjecture can say something about high-boundedness. And also, maybe we can explore some more connection to other branches of mathematics. So finally, I would like to say that the graph coloring problem are generally hard to solve, but I still love doing mainly because that this problem is really not about local information. It's about the global structure. But I still love doing it because it has a lot of fun. So let me end my talk by challenging you the following graph coloring problem. Okay, thank you for your attention.